Good afternoon, everyone. Thank you, Andrew, and thank you for coming. Okay, our work is about how we can use a simple and old idea from statistics to help us interpret today's black box models. This is joint work with my advisor, Percy Liang, at Stanford. Over the past few years, as you know, we've gotten quite good at building machine learning models that are accurate on a lot of different tasks. However, these models can be very complicated, with hundreds of thousands, if not millions of parameters. And it's hard to know at the fundamental level, what are these models doing? Why are they making the predictions that they do? That's going to be the focus of this talk. Given one of these models and the prediction that it makes, can we answer the question, why did the model make this prediction? If we can answer this, then we can make better decisions given the predictions of the model. We can improve the model, discover new principles about the world, and simply provide good explanations to consumers of these predictions. Just to ground us in a concrete example, here's a picture of my dog, Coda, and here's a model that takes in this picture as input and outputs a prediction, in this case the label dog. We want to ask, why did the model, after seeing this input, make this prediction? Of course, this is not a new question, and the hardest part of answering it is defining why. What does it mean to interpret a model? There's been a lot of great work on this. For example, you could ask, which part of the input is most responsible for the prediction? And if you were at Bean's great tutorial yesterday, you have seen many more approaches. These methods have led to a lot of useful insights about our models. However, they all treat the learned model as fixed. So they don't really help us if we want to know, well, where did this model come from in the first place? The answer to that, of course, is the training data that the model was learned from. In some sense, the ultimate reason for the prediction lies in the training data. And so that leads us to the question, can we then give an explanation of a prediction in terms of the training data? That's the approach that we're going to take. We think is complementary to a lot of the great work that's been done in the space. Okay, so before we go on, let's set up some notation. We have training data Z1 to Zn, where each Z is a pair X, Y. X is the input features, and Y is some target, like a label. As usual, we want to learn a model from this data, so we can pick a loss function, L, and find the parameters that minimize this loss function on the training set. Now, we want to find the training points that were most responsible for a given prediction. To do this, we're going to take our training examples one by one and upweight them by a little epsilon so that the model tries harder to fit it. Concretely, this means that we add a term to our objective function, epsilon multiplied by the loss at the training point that we're upweighting, and that gives us a new set of parameters. We can then see what effect this change in parameters has on the prediction. For example, we can measure the change in loss on the test point between the new parameters and the old parameters. And if this changes by a lot, we say the example has high influence. By computing this for each training point, we can then find the ones that have the most influence on a particular prediction. All right, so let me just recap. We started off with this question, why did the model make the prediction? We noted that the model comes from the training data, and we formalized this notion by asking the counterfactual, how would the prediction change if we upweighted each training point? Okay, so that's going to be the core of our approach. Now, how do we actually calculate the influence of each training point? Naively, we could retrain the model after upweighting each different training point, but that's going to be too slow. Fortunately, there's a closed form expression given to us by the framework of influence functions. Influence functions were introduced in the 1970s in the field of robust statistics. There's a lot of rich history here and connections to leverage, actually, that the previous presenter talked about. Here, we're just going to take one very basic result from that work. So our goal is to measure the influence of a training point on a prediction. And if you recall, we defined that as the change in loss on that prediction as we upweight the training point, rather we increase epsilon. And that in turn changes our model parameters accordingly. The trick here is to let epsilon go to 0. So we add just a very little bit of weight onto the training example, Z-train. If we do this, we can then define the influence of upweighting Z-train on the loss at Z-test to be the rate of change of the loss on Z-test as we increase epsilon from 0. We can evaluate this by taking Taylor expansions because we are in this asymptotic setting. And we obtain this quadratic form where H is the empirical Hessian matrix. This essentially measures the similarity between the test point Z-test and the training point Z-train under a metric that depends on the model. And in fact, if the model is well specified, then this matrix H is also the Fisher information matrix. And this is a pretty standard derivation that you could find in a lot of stats textbooks. Okay, so now that we have this formula, what does it look like when we apply this to a real model? As an example, we trained 2 different models on an image recognition task of determining if a picture is a fish. The first model was an RBF SVM trained on raw pixels. The second, logistic regression on top of an inception neural net. Both models got this prediction correct, but they arrived there in quite different ways. And we can see this by looking at the most influential training examples for each model. As you might expect, the SVM on raw pixels is doing a soft nearest neighbor approach, and it relies, therefore, on training data that is superficially similar to the test data. Right, dark background, some orange stuff in the middle. On the other hand, the neural net model picks up on training points that are more semantically similar. And the upshot is that by looking at the training data that the models base their decisions on, we can get some insight into how these models operate. Before we move on to some applications, let me go through some potential issues with this. First, it's just really slow to evaluate the expression that we just gave. This is mainly because of the inverse Hessian term, which takes time cubic in the number of features to compute. To get around this, we use the fact that we can quickly compute Hessian vector products without explicitly forming the Hessian. We can then use these to efficiently approximate inverse Hessian vector products, which are all we need for our calculation. Essentially, we can use a collection of known tricks from the optimization literature, references are there, to help us out here. Secondly, sometimes our losses are just not smooth, and that's a problem for differentiating them. At least in the case of the hinge loss, we found that we can use a smooth version of the loss just for the purposes of calculating influence, and it seems to work quite well empirically. The third and probably the biggest problem is that we have implicitly assumed we can find the parameters that sort of globally minimize the training loss. Of course, this is not often possible to do. Your problem might be non-convex, you might have early stopping, and so on. And in general, you normally end up with parameters that are not quite the global minimum. On the bright side, if we do end up at a local minimum, then influence functions still tell us what happens if you retrain the model starting from that local minimum. So it's not perfect, it still tells us something meaningful, but whether we can do better, I think it's an open question and good direction for future work. Just to convince ourselves that influence functions can still work in these settings where their assumptions are slightly violated, we compared what actually happens if you remove the training point and retrain your model to what we predict would happen using influence functions. By and large, we get very good agreement. So on the left, we use the fast stochastic estimation of the inverse Hessian. In the middle, we train an SVM with a hinge loss. And on the right, we train a non-convex CNN. Okay, so finally, let me go through a couple of concrete applications. Percy told me to add some pictures to my presentation, so I don't know if this is what he had in mind. The first application is debugging model errors. If a model makes a mistake, can we find out why? Our case study here is hospital readmission, where the task is, can we predict if a patient will be readmitted within 30 days of being discharged? We intentionally screwed up the training set so that our model would make some errors, and we asked if we could pinpoint the reason for these errors after the fact. In particular, we set up a domain mismatch, which is not uncommon in medicine, by removing almost all of the healthy children in the training data. In fact, we left only 4 children in the data, 3 of whom get readmitted, and so the model now wrongly thinks that children get readmitted to hospital frequently. As you might expect, this causes the model to make some errors on children in the test set. Now, say you're a model developer who has found such a mistake in the validation set, for example, and you want to find out why. One thing you can do is look at the feature weights. This is logistic regression, so we can eyeball the coefficients. But the coefficient for whether you're a child doesn't actually pop out in this instance. However, if we look at the most influential training examples on this prediction, we see that the 4 children in the test set are an order of magnitude more influential than any other point. Moreover, if you look at the reason why they're influential, for example, you can take the gradient of the influence with respect to the training features. And if you do that, we see that they're influential because they are also children. And so with this information, a model developer can hopefully dig in deeper and find the root cause and try to fix these sorts of problems. Second application is fixing training data. Just because of time, I'm going to have to skip this, but it's on our poster and our paper. I want to get to the third application, which was quite an unexpected one for us. So recently, there's been a lot of interest in test set attacks. Right? There's a NIPS competition, and basically what happens is an attacker modifies the test data in order to make the prediction wrong. In fact, Ian Goodfellow and other researchers have shown in a series of very cool papers that you can often trick an otherwise highly accurate neural net by making a carefully chosen but visually imperceptible perturbation to a test example. These are called adversarial test examples, and one way to construct them is to follow the gradient of the test loss with respect to the test input. In other words, we modify the test input in the direction of the largest change in the loss. So we have adversarial test examples. Can we create adversarial training examples, where a small change in a training point can screw up a prediction? So that's the question we set out to ask. The natural thing to try is to just copy what worked, follow the gradient of the test loss, but instead of doing it with respect to the test features, we do it with respect to the train features. In other words, we modify the training data in the direction of the greatest change in test loss, right? Assuming we know the test example. It turns out that influence functions can help us calculate this gradient because essentially we're studying the same thing. What happens to the prediction as we play around with the training set? And I just want to note that this is what we end up with is mathematically equivalent to what others have derived in the context of different models and different data sets. And in those cases, they did so directly without going through the influence framework. All right, so does this actually work in practice? Our setup was a simple binary classification task where you try to tell if an image is a dog or a fish. Something you hope you wouldn't be able to get too wrong. And we did a logistic regression model, as usual, on top of inception features. Surprisingly, we found that if you choose the training example carefully and you choose the perturbation you want to add to it carefully, a small change in this training example can actually flip the prediction on multiple test images at the same time, demonstrating that these attacks can actually be quite dangerous in some settings. There's a lot more to study here and talk about. I'm happy to do so offline. Let me just conclude this presentation. So we started off by asking, why did the model make this prediction? We noted that the model comes from the training data, and we formalized this idea by asking the counterfactual, what happens if you change the training data? Hopefully we convince you that that's at least a reasonable idea, and that in fact we can better understand the model's predictions by looking at how it was derived from the training data. Influence functions let us do this efficiently by differentiating through the training process. There's a lot of directions for future work. For example, we relied on making infinitesimal changes to epsilon in order to get a closed form expression. Can we study what happens if we make larger, more global perturbations? What happens if you remove all patients from a given hospital? Can we say anything about that? What if you have a large non-convex model, you run SGD a few times? What does influence mean in that regime? So this is just one step in this direction. I think there's a ton of good work that's yet to be done and further developing tools for better understanding black box models. With that, thank you for your attention. Our code and scripts to reproduce our experiments are all up online. Once again, this is joint work with my advisor and my dog who graciously contributed part of our data set. And we'd like to acknowledge funding from the Future of Life Institute. Thank you very much.
Thank you, Peng Wei. Any questions?
So if you say that you have logistic regression on top of ImageNet features, you really have two training sets. You have the training set, the dog versus fish, and you have the training set that you got your features on. And can you tell anything about the examples from this feature training set?
Yeah, that's a great question. So implicitly, we are assuming that the ImageNet features come from a really large training set, for example, maybe millions of examples. And we do what I guess is commonly done, just take the bottleneck layer and you specialize it to a particular problem. You would hope that a small change to one training example would not actually change the ImageNet features that much. This is just a guess. So it's possible that you could get even more leverage with these training set attacks if you're allowed to change all of these features. And I think that's a good question for follow-up work. It's hard for us to do in this incarnation because there are like all these scalability and non-convexity issues that we have to think about. Like if you have dropout, if you have early stopping, what does influence mean? Thanks.
So another goal of robust statistics is to design robust procedures by choosing different losses, maybe so that it cannot be influenced by adversarially chosen small proportion of examples. Is there any? Do you have any insight on that direction? Or?
Yeah, that's a great question. So you could use this sort of diagnostically, I think, by if you have a given model, you can sort of evaluate how robust is it to, say, adversarial training attacks by measuring the magnitude of the influence function. And that gives you some sense as to, well, is my model vulnerable? Maybe if I change the loss and I remeasure this, maybe it'll be better. So in that sense, I think it's a good diagnostic. You could also think about regularizing the influence as you are training the model. I think there are some papers that implicitly do something like that. So that's also potentially something we could do.
Any other questions? Maybe I'll ask one last one. So you have to compute the inverse of this Hessian, and it could be the case that that's singular, and particularly for deeper models. So is that a problem, or is that...
Yeah, that's definitely a problem. And so that relates to like what happens if it's not convex as well. In our case, for the CNN, we trained a CNN not to convergence. The Hessian there had negative eigenvalues, and it didn't really make sense to calculate influence. What we ended up doing was just adding a large damping term, so a big quadratic bowl, and that actually seemed to work in the sense of empirically predicting what would happen if you remove the point and retraining it. So it seems to work. It's not super satisfying, and I think just generally, as I said, exploring what happens with these larger models where you end up at sort of weird points. Can we characterize like what happens in those situations?
Great. Thank you very much.
All right. Thank you.